we had so yeah, yesterday we had talked about signal spaces and we had stopped at this point. So again, let's resume. Let there exist set of night energy signals. Let there exist a set of finite energy signals phi and t n equal to 1 to capital K that are orthonormal sense that fine, and we can express any arbitrary st using linear of signals as s hat t equals summation k equal to capital K S K. Right? So sorry, not SKT, simply SK, where shunts SK are selected to minimize error. Fine.
Sir,
Yep.
there would be only one possible values of ST, right?
Yes, we are coming to that.
Okay.
Okay. So you want to minimize this error. So if you want to express ST in terms of these 5Ks, you have to minimize this error, and so you have to minimize.
Sir,
Yep.
sir, you have written we can express any arbitrary signal st. So the representation that you have written, the summation of sk phi kt, is that the exact representation of st or is it an approximate?
Uh, right now we are treating it as an approximate.
Okay.
Okay, we'll come to any arbitrary energy signal. So we are only talking about energy signals. So since this is an approximate representation, we are talking about the error. So norm square of S tilde, this is the norm square of S tilde t equals minus infinity to infinity st minus summation k equal to 1 to capital K sk. Right? Now, how do I minimize this? You
Differentiate
remember the
and
principle
zero.
of orthogonality?
Yeah.
Yeah.
So directly invoking the principle of orthogonality means that this error term, so for minimum error S tilde t phi k t equal to 0 for all right. This is what we called the principle of orthogonality in the previous classes.
Yes. Yes.
Yes, so means minus infinity to infinity
Sir,
S tilde t.
uh,
Yes,
in principal orthogonality, shouldn't we be using the IAP means that because S tilde t or phi k t may not be zero, it may not be equal to zero, but their inner product may be zero.
this is the inner product. This is the inner product. This is how we defined the inner product.
Oh, for signal, sorry.
S tilde t. Oh, sorry. Or for minimum error, these should be orthogonal. Sorry, my bad. Instead of equal to, I shouldn't have written equal to 0. Right? Agreed?
Yes, sir. Yes, sir.
These are orthonormal. So phi k's are orthonormal. So you get this, or Sk is the projection of right. And consequently, S hat T is the projection of St onto the signal space or onto the k dimensional signal space spanned by phi 1 t phi right. And S tilde norm square min equals so again from the principle of orthogonality or from what we have done for what we have done for filters matrices, we can use those results directly and say that right. This makes sense.
Sir, this is small k equals to 1 to capital K, right?
Yes.
Okay.
Or rather norm of st square minus summation k equal to 1 to capital K. And if st belongs to right. Makes sense.
Yes, sir.
Yes. Consequently, right? Is the vector of coefficients of, sorry, it was 5. Then as the n tuple. Let's not use the term vector, or rather, let me do it this way. Let me, okay. Let me write it like, just to clarify the difference, or just to, yeah, so let me first write the word vector. Vector. But so this is what we wanted to use the red one here. So this is an n tuple. So ES equals this equals the norm of this n tuple. Now it has turned red. Fine.
Yes, sir.
Fine. Vashish,
Yes.
makes sense. Now for the even more interesting part. So let us have two signals S1T and S2T contained within the span of fine. Then S1T equals summation K goes from right. This is right.
Yes, sir.
Yes, sir.
Yeah. So now S1T or rather, let me do it this way. S1t, S2t. This inner product equals S1t, S2t, dt. Right? Equals summation k goes from 1 to capital K, S1k phi kt k goes from 1 to capital K, S2k conjugate phi kt dt equals the integral k goes from 1 to capital K.
Sir, won't the phi k have any conjugate part?
Yes, it should be conjugate. L equals 1 to capital K, S1k, S2L conjugate, phi k t, phi conjugate LT dt. Since integration and summation are both linear operations, I can change the order of integration and summation. This becomes summation k goes from 1 to capital K, L goes from 1 to capital K, S1k, S equals k goes from 1 to capital K. S. Right? Right? Any problems with this?
No, sir.
So if we can express signals from a signal space as vectors, can we can express or the of k tuples, capital K tuples. Right? So all you have to worry about now is multiplying the coefficients rather than multiplying the signals themselves. Or instead, so we have actually reduced the operation of integration to that of a vector multiplication or vector inner product. That makes life simple, doesn't it?
Yes, sir.
Yes. So this has made life slightly simpler. So let us now do something related. So let us now have capital M finite energy waveforms out of which we want to construct an orthonormal basis. So we want to construct an orthonormal basis out of these, and we have S1T till S capital MT. So how do we do this? So say going back to your first year course, I have a set of M vectors and I want to reduce it to a set of M orthonormal vectors or basis. I want to find an orthonormal basis for that. How do I do that?
Sir, we would take any particular vector and then we would project it onto another, and then we'll pick another vector, we'll project onto the first and then subtract
Yes,
it
yes,
to
yes. You
get
are
the best.
telling me the procedure. Does anyone remember the name of this procedure?
No, sir.
No. Strange. So this procedure is called the Gram-Schmidt now do you remember?
Yes, sir.
Yes, sir.
Yeah. So now, so let phi1t equal S1t divided by fine. Let C21 psi2t phi2t. Fine. In general, or by mathematical induction, whichever way you prefer. C Ki I less than K equals minus infinity to infinity SKT T dt psi K T equals SKT minus summation I goes from 1 to K minus 1 CKI phi IT and phi KT equals psi KT divided by norm of. Fine. And I believe it is trivial to show that phi KT and so phi KT and so this these two are trivial, I believe.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes. Therefore, hmm, working. Scroll isn't working. So yeah. Therefore, can represent the signal SMT as a vector SM, sorry, SM in the n dimensional signal space spanned by. Actually, I am also used to the notion of, or I'm also used to uh, saying vector instead of n-tuple. So here actually I mean n-tuple. So we since the interpretation of n-tuples as vectors is so common that subconsciously when I say vector, I do mean an n-tuple, but I hope most of you by now understand that a vector and an n-tuple are two different ideas. Hmm?
Yes, sir. We do get it.
Yes. So here I meant a vector. So just if I make that error somewhere, just point me. I'll correct that to an n-tuple. So in the n-dimensional signal space spanned by phi 1 t to phi n t, where n is less than or equal to m. Also, it is important to note that had we chosen phi1 equals S2T by and switching S1T and S2T process phi1T. The basis phi1T would still be n-dimensional, but not the same as obtained right.
Yes, sir.
Yeah, so Smita asks, what does the subscript 2 represent? Where, Smita?
So in the norm of 5k square expression is equal to 1.
5k. Oh, the lower two. Oh, okay.
Yeah,
So
yes.
I'll come to that in a minute.
Okay.
So I should have specified that yesterday. This is also, I'm used to writing it like this. It's not something that I wanted to write. I'll come to that. So let's finish this discussion first and then I'll talk about it. Fine. So the point that I want to make here is that the basis obtained via the gram process are not unique. Fine. The bases are not unique. And therefore the representations of these signals are also not unique. But the only thing that we have is that it will form an n-dimensional space. Fine. Okay, guys.
Yes, sir.
Yes, sir.
Yes. So, and now let SMT equals the real part of SMLT e to the power j 2 pi f naught t. So anyone remember low pass equivalents from previous semester? So this SMLT is the low pass equivalent of SMT. You remember the low pass equivalents?
Baseband signal.
Yeah, low pass or baseband equivalent. You
So
remember these?
we didn't know if that was the like the original signal were band pass. Like we
Huh?
had no idea. We had no idea that the original signal were band pass.
No. That is not. So this is Gram Schmidt is done.
Okay. Yeah.
Okay. I'm just asking whether you remember low pass equivalents or baseband equivalents.
Yes, sir, we do remember.
Okay, great. Those who do not remember, please go back and look at those lectures today. We will be using baseband equivalents or low pass equivalents extensively throughout this course. So please go back and revisit those things. So now let S be then is trivial, show that SMT are also forms an orthonormal basis for set of baseband signals phi and t. Also forms a set of passband signals. Fine. You can actually show that if the baseband equivalents are or the baseband signals are orthonormal, then the passband equivalents will also be orthonormal. It shouldn't be hard. Or should I do that?
No, sir, it's okay.
Yeah, this should be trivial to prove, but also one important or rather something important. As usual, the ink color change is delayed. If phi NL T is an or rather if NL T is contained in the span of then SNT or phi K SNT may or may not be in the span of or in span phi K T. Fine. So if a signal is in the span of the low pass equivalents, its band pass version may or may not be in the span of the band pass signals. Fine.
So what if the span of phi KLT forms a orthonormal basis? Then
Yeah, that is so the span of IKLT, if it forms an orthonormal basis, then the span of IKT will be an orthonormal basis. That we can show easily. But one signal that is in the span of the baseband signals may not lie in the span of the passband signals. It may lie in the span of it may require some more signals, or it may require some more signals to express itself properly. So you cannot. So the only what I am pointing out here is that if you have that, okay, this is a span. This signal lies in the span of the baseband. So I can say that the passband signal lies in the span of the passband versions. You cannot automatically say that. You have to prove that. That is the only caveat here.
Okay, sir.
Fine. So now, oh, we finished faster than I expected. So now I'll turn to Smita's question. So okay, the ink color change hasn't again. So let's take this example, vector x in right. Then or rather right, this is how we define the length of the vector. Right, Smita?
Yes, sir.
Yes, this is how we define the length of the vector. Now, this is called the small l2 norm. Equivalently, this thing xt square minus infinity to infinity dt. This is called the energy, or and the square root of energy of a finite energy signal, or the square root of the energy of a signal is called the capital L2 norm of the waveform. That's why if you remember, I sometimes write L2 signals for energy signals. So now, however, coming back to norms, so in general, the P norm of a vector is defined as summation P goes from, or rather K goes from 1 to capital N xk absolute value to the power k under the kth root, or rather, since we can, oh sorry, to the power p 1 over, and this should be p, k equal to 1 to capital N xk to the power p whole to the power 1 over p. Fine. So that's why I wrote that p here.
Okay, sir.
Okay, now since we have some time, let me define some interesting cases. So if, let's say, L1 norm, L1 norm is simply the summation of the sum of the absolute values of the vector. Fine.
Yes, sir.
Yes. And 2 norm we know. Let's look at the two most interesting norms, or the two extreme cases. The L infinity norm. Any guesses? How do I calculate this?
Max value.
Yes. So L infinity is the max of, sorry. So we have to the maximum value. You can argue this that you raise everything to the power infinity and take the infiniteth, or take the 1 by infinity root, and then you take the maximum value outside, and everything is basically 1 plus something less than 1 raised to the power infinity. So that maximum value survives, and everything else goes to 0. That's how you take this logic. So, or max of x. This is the maximum value. So this is the infinity norm, and there is something called the L0 norm, which has recently been quite popular. Number of non-zero entries in X such that xk to the power 0 equals 1 if xk not equal to 0, 0 if xk equal to 0. So you define the you so 0 to the power 0 is a, or 0 to the power 0 is one of those undefined quantities. So here we do some sacrilege and define that 0 to the power 0 as 0, or force 0 to the power 0 as 0, and define the L0 norm. So has anyone heard the phrase compressed sensing?
Yeah. Like basically they reduce the number of features.
No, compressed sensing is not reducing the number of features. Compressed
Like
sensing,
basically encode a larger dimension into a smaller dimension. Like we can use L1
yes,
norm to
yes,
do
or
that.
simply stated, there are certain signals that if you can you can sample at rates below the Nyquist rate and get away with it. And in that compressed sensing, this L0 norm plays a big part. Fine. So this is the story of the norms, or different norms. There's one more thing. So for a matrix, say I have a matrix A. Do not do this mistake just for that. I have a matrix A, and I want to know summation k equal to 1 to, say, A is m times n. And I want to know summation k equal to 1 to m, L equal to 1 to n, A kl square. Then this is called the Frobenius norm of A. Not this is not the 2 norm of A. because the matrix norms are defined in terms of their eigenvalues. The infinity norm of a matrix is its maximum eigenvalue, the minimum eigenvalue, the trace. The one norm is the absolute value of the trace of the absolute value and all that. So the norms of a vector and the norms of a matrix are different ideas. So do not confuse this. This is called the Frobenius norm of a matrix. Fine. So any doubts with this? Okay, then we will stop here and continue tomorrow.
Yes, sir.
Sir,
Excellent.
distribute the note, today's notes.
Sorry?
Sir, could you
Yeah,
distribute today's
yesterday
notes?
there was some error. So it's showing an
Okay.
error. So I'll share yesterday's notes as well.
Okay, sir. Okay. And sir, one more thing.
Yeah.
Which book are we referring to right now? I mean,
Right now the same Procus and Salehi.
okay, okay.
Okay, so what? So the textbook is Procus and Salehi. Just that these vector spaces, I like Gallagher's treatment for them, because Gallagher's treatment is more abstract, and I believe that something like vector spaces should go through Gallagher. So right now, if you look at what we have done, I'll point out the topics. You can possibly note them down. So chapter 6, we have done 6.6, that is waveform coding, slightly detailed version of that. So we have done 6.6, and then after 6.6, we are right now at 7.1, which is geometric representation of signal waveforms. Then we'll go to pulse amplitude modulation, two-dimensional signal waveforms, multidimensional signals, and optimal receivers and all that stuff. So this chapter
So this is
7 will
from
take.
the
Sorry?
by this is from the digital communications by Procris Salai, right?
No, no, no,
Or
no,
from
no.
the
Don't refer to digital communications by Procus. It's the same book, Communication Systems Engineering,
okay,
that we
okay,
started
okay.
in the previous semester. You remember we used a communication systems engineering book in the previous semester.
Yes, sir.
Yeah, the same book, because digital communications by Procus is it's the same authors, but that book is ridiculously hard to read. While this book is
Okay,
much simpler to read. Fine.
This week we have the quiz, right?
Yes, this Saturday,
Okay, sir.
5 p.m. Okay then. Bye. Have a nice
Bye.
day.
Bye, sir.
bye, sir. Thank you.
Bye.